As an application of the use of Ampere-Maxwell law, let's solve this equation. Actually, this is the only type of equation that we can ask in these kind of, well, for this phenomena, because so at any rate, of course, we have to have some kind of a symmetry for to be able to compute the corresponding magnetic field. And so as a result, this is the only kind of problem that can be asked in here. So that's essentially what we have discussed before. So we have a capacitor. It's a parallel plate capacitor, but the capacitor plates are disc shaped. So that's necessary because somehow we should have these rotational symmetry, part of this cylindrical symmetry in there. So as a result, we have this, all right? There is this current I flowing to the to one of the plates, and so therefore the same current is continuing in here, but we know that there's no current between the plates, obviously. Now consider a point between the plates, which is at a distance r from the symmetry axis. Let's just remember that there's a symmetry axis in here, so the symmetry is very important. From the symmetry axis, and find a magnetic field at this point for these two cases when the, of course, this the point is basically between the plates, and for the case when the point is slightly off or way off. In any case, so this is the situation. So that's basically the part A of the problem. I'm exaggerating things in here. So normally, of course, the distance between the plates is much smaller than the size of the plates. Just keep this in mind. But of course, to be able to draw the pictures nicely in an understandable way, I need to exaggerate in here. So just keep this in mind, because if the separation between the plates is large compared to the diameter of the plates, then we cannot use this parallel plate formula. We cannot assume that the plates are almost infinite. So this kind of an assumption will not work. So our results will not be valid in that case. Okay, so just keep this in mind. So I'm also, if there is some kind of a person in here, let's see. I mean, this person, for example, when he looks at this picture, he's going to see this diagram in here. So as a result, sometimes I'm going to talk about this kind of a picture. So this big circle is the plate, and I'm considering a point in here, but that should be between the plates. So what's the magnetic field at that point? So the part B is this, basically. It's the same situation, except that the point is now outside the plates, right? Let's just go ahead and do it. What we do is this. We're using the symmetry arguments. So since I would like to compute the magnetic field at that point, I choose an Amperian loop that's passing from this point. But the Amperian loop, of course, should have the same symmetry as the symmetry of the problem. So therefore, it has to be a circle. Why? Because only in that case, I know that the magnetic field at all points on that Amperian loop has the same magnitude, and it's also always tangent to the Amperian loop. So by using this, let me first write down the equation for the Ampere's law and Maxwell's addition to that. So that's mu 0 epsilon 0 d phi e over dt. That's the electric flux. So let me write EL in there. So in this case, of course, there is no enclosed current, and everything is coming from there. Everything is coming from this electric flux, the rate of change of the electric flux, and we would like to find it. Okay, so, but you can see that the electric field is everywhere in here. The electric field is everywhere in here. So all of these electric field lines will actually appear like dots in here, because they are going to be pointing towards us on that picture. So there are electric fields outside and inside, but only the inside electric field contributes to the flux. So as a result, I'm just going to, yeah, why not? I'm going to do it in that corner. So the electric flux, therefore, is equal to the area of my Amperian loop, or the area of the surface enclosed by the Amperian loop is pi r squared. Little r is just the distance of my point from the axis, symmetry axis, multiplied with the electric field. Now, what's the electric field? I can use the parallel plate formula now. So that's the point where that's the part where we actually use the fact that the separation between the plates is very small, and I know that this surface charge density is basically the total surface charge divided by the total area. So therefore, this is pi r squared, and capital R is just the radius of the disk. So in this situation, therefore, the electric flux is equal to pi, there is no pi, sorry. There's no such pi. Q divided by epsilon 0 times r squared divided by little r squared. All right, so as a result, on the right-hand side, therefore, I have mu 0 epsilon 0. I have a rate of change of the charge, so that's therefore dq over dt. Let me erase this. So I'm still talking about the second term in here. So let me complete this equation. There was 1 over epsilon 0 in there, and then little r squared divided by capital R squared. So this is the term that's coming from the from Maxwell's contribution. All right, so that's the electric flux thing. So for the case of magnetic line integral, we have gone through these kind of arguments before when we were discussing the Ampere's law. There's this symmetry argument in there, so because of that you can then replace this dot product of the magnetic field with the displacement by the product of the magnitude. So you just replace this b dot dl with magnitude b times magnitude dl, and then you say that the magnitude of b is constant, so therefore you take it out of the integral and so on. At the end, we get in here as the answer in here is mu times b times 2 pi r, and so therefore I'm going to pass to the new page now. So b therefore is equal to 1 over 2 pi r. There was mu 0 epsilon 0, and then the rate of change of the, let me write this thing down like that, 1 over epsilon 0 r squared over r squared. Let me also check one more time if everything is correct. Yeah, it seems to be correct. So what happens is that this is basically the current. Epsilon 0 goes away, and so therefore the magnetic field is equal to mu 0 divided by 2 pi little r divided by r squared, and let's not forget the current. So that's the situation when the radial distance of the point from the axis is less than the radius of the plates. Okay, so that's for this situation. Let's then quickly go ahead and do this one. What happens if the point is outside, or the distance of the point from the axis is bigger than the radius? So again, the choice is the same. So geometrically we choose the Amperian loop like that. Let's choose it like this. So the Amperian loop has a radius which is little r, but who cares what that thing is? So we know that the electric flux is basically only between the physical plates, so therefore the flux is over that region only. So in that case, the electric flux is basically the area of the plates this time, not the area of the enclosed surface, but the area of the plates multiplied with the electric field. Electric field is sigma over epsilon 0 again, and sigma is charge divided by pi r squared. So therefore the electric flux in that case is equal to Q divided by epsilon 0. You might think that this might be some relationship with the Gauss law, but just keep in mind that this is not an enclosed surface. This is not a closed surface, sorry. We express the Gauss law for a closed surface only. Here this is just an open surface. What is that surface? Let me use the red color to color it, it is basically this surface in here. So it has a boundary, and the boundary is the Amperian loop, right? Or it is that surface. But of course, you can close that surface and then just verify that this is really you can also find this relationship by using Gauss law as well. But I'm not going to do this kind of a thing. So in any case, let's just do again. So b dot dl integral. Let me continue this with the next page. Sorry. So I'm going to add a page in here. So therefore, let's just write down the Ampere's law and then add Maxwell's contribution to it. Enclosed current is equal to 0, and flux is the electric flux. I forgot again, so that was Q divided by epsilon 0. So let me also correct this. So therefore, this is 1 over epsilon 0 dq over dt, but dq over dt is the current. Epsilon 0 goes away, so therefore we again get mu 0 times I. So the left-hand side is again b times the circumference. So therefore the magnetic field in that case is equal to mu 0 I divided by 2 pi r for points outside. So let me just summarize both of them. So the magnetic field is therefore equal to mu 0 I divided by 2 pi little r divided by r squared for a point inside, and mu 0 I divided by 2 pi r for a point outside. I can also draw the dependence of the magnetic field to distance. Let me use a thick yellow curve. So inside, therefore, the magnetic field increases linearly with distance, and outside it has this typical 1 over r behavior. So it just goes to 0 continuously. It is nice to check that, of course. Right at the center, the magnetic field is 0, so that's the center of symmetry. So the 0 is the only possible value. It is also nice to check that the magnetic field is continuous. So it just changes basically continuously. There is no jump discontinuity in there. As a result, this is essentially the magnetic field produced by a thick wire that's carrying a current, essentially. The only difference in here is that physically, of course, in here, there's no current in that region. There's no real current. It's just that there's an electric field which happens to be changing with time.